let me just start by giving you a tour. If you pull up the web page, um, so we'll see there's quite a bit of material. We're not going to go through all of this. It'll be selective. But there are a variety of Python tutorials. They're numbered 1 through 5. So start with number 1 and 2. That should be pretty trivial. Number 3 is sort of interesting. It actually downloads the OHA PDF, compiles it inside of Colab, pulls the fragmentation function, and then makes a real pi decay graph calculation that you can compare with data. And then I'll get to these later. So these are all Python-based. If you prefer Mathematica, this will give you some tools to work with partial distributions and fragmentations inside of Python. But if you want to do Mathematica, there's this main parse subdirectory that has quite a bit of things, and I'll get to the rest later. So let me start by just sort of catching up on where we were last time. So these are the notes from last time. We did xFitter, and we were looking at strange distribution. In particular, we were using the WZ data from Atlas, and that we found that the strange, well, we got about 110%, depending on exactly how you do it. They get between that and 120%. But again, that, even though that wasn't a real fit, you could turn on Minuit and verify that I really was at a minimum. And so this Atlas data really does seem to be pulling things up to a higher value. And so here are the results. When we fixed, so let me actually go to the next one. Here we go. When we fixed the strange ratio to be 1/2, which is what you expect from fixed target, we did that. And then when we let it free, we got 110%. And then here are the chi-squareds. If I fix it, I get 1397, and it drops by over 150 points. So it really does seem to be preferring the largest range. So what are we going to do now? We're going to do some applications. And mainly, I'll show you some tools to deal with PDFs and fragmentation in Python Mathematica and other things. So I've got 1, 2, 3. 1 is just an absolutely trivial example. And then in number 2, what I've done, so you don't have to interface external files, I've pulled in the partial distributions at a fixed Q at 10 GeV. And so here it is at 10 GeV, the fixed and free. The free is a little bit higher, but it's not as dramatic as it was at 2 GeV at the start. So the evolution sort of closes things up quite quickly. So just to make it simple, I encapsulated that. And then you can calculate the parton momentum fraction by doing simple integrals. Again, here's the xFitter. This is at the initial scale of q squared to 1.9, and you see it really is a factor of 2 between the strange. So that's why I picked this tutorial, because it was quite dramatic. And so, okay. And then again, these are some other things you can do. I'll leave this in the notes. But then once you get in a real set of partial distributions, you might try making this graph. This is interesting because it's the momentum fraction of all the flavors as a function of Q. And so you can see here the charm turns on and the bottom turns on. And in fact, you can have the top turning on. And then as you go out to high scale, this is U bar, D bar, S bar. They start to go, symmetric in the high energy limit. And then you've got the whole spectrum. So those are the kind of things you can take a look at. Also, we can do nuclear correction factors. You can pull in some nuclear PDFs. So, and then if you want to do Mathematica, main parse, which I showed you is in the directory there, that's a Mathematica reader at each of the LHA PDF files. And so you can do that. And those are the details there. So let's go ahead and try things out. And just to start, I will go ahead and run this. This is one of the trivia ones. And I import a few things. You see, in particular, I've commented out the LHA PDF because that's not native to Python. You have to compile that externally, and that takes a little bit of work. But And you can see I've stored the PDFs in here. I've just stored them in a big table to make it simple, just get things up and running. But oops, okay. Yeah, and then here are the values and some plots. So here it is at 10 GeV, and so I've divided the gluon by 10, and it still kicks up a high X. And then you can do some integration. I've used the Simpson integration. And so I've just done that over the grids. And here it is, I go from minus anti-top up to top. So this is top, T bar, B bar, S bar, C bar, S bar, D bar, U bar, gluon 44%, and then down, up, etc. And then if you add that up, check the momentum sum rule, you get 99%, which is 100% within round off. So that's pretty simple. And if you're familiar with Python, you can skip over that. Let's try something a little bit more interesting. I'll run this one and make sure I kill the old. Okay. All right. And again, here I've stored the PDFs. And in this case, I've stored both the fixed flavor and the fixed ratio and the variable ratio. And so there it is. And how this is the RS fixed and RS free that I showed you before. So everything's in these, it's completely done for you. But if you want to vary them and try it out, in this, because I imported them, I only have the PDFs of Q of 10 GeV. So you can't do anything else here, but you can do integrals and things like this. For example, here are the momentum fractions of the two, and you see the sum rule checks. One thing you might want to calculate is that ratio, S plus S bar over D bar plus U bar. If you want to try that out, that's fairly simple one for you to try. But these are sort of warm-ups. Now, number 3 is a little bit more interesting. And I found this on the web. I do not know who made this. I wish I did, so I could give them credit, but this is quite elaborate. So let me start by making sure I have a clean slate. I'm going to kill my current sessions because this will take a little bit of CPU. And I'm going to run the whole thing. But what this does is it's going to go to the LHA PDF website, and it's going to pull down the code that does the LHA PDF interpolation. And that's a C code with Python hooks. And so it's going to download that and actually compile it inside of Colab. So this will take about 15, well, maybe 10 minutes. It's going to take a while because this is pretty big, but what it will do is it will build the Python hooks for Colab so that the Python can talk to the LHA PDF. So before, about a year ago, this was really the only way to get the full set of PDFs inside of Colab. But there's one more way, which I'll show you in examples 4 and 5. So I'm going to let this run for a little bit. But if you want, you should be able to download this, fire it up, because this one is a little bit more interesting than the first 2 warm-ups. As I said, it'll take a while. It's really slick that it downloads and compiles it and makes the LHA PDF library, which is what it uses to read the PDF grids. The downside is that Colab is volatile. So when you close it, it's gone. And then if you get something, you get a nice spot and say, gee, maybe I should have done it this way. You got to load it up, wait 15 minutes to recompile. And so it can do lots of things, but once you shut it down, it's gone. So that was the best we had a while ago, but 4 and 5, I'll show you some other options. So this will go for a while. And then you see in the second one here I am able to import the LHA PDF library tools, which is what we use to read the grid files. So. And we're getting close, but it does take a while. And again, so, these are examples for you. Feel free to play with them. If there are specific things you want to try or something that's useful to you. But the goal is when you leave here, you've got a number of tools so you can pull up PDFs, integrate them, slice and dice them, calculate cross sections with them. Same with fragmentation functions, and just tools to access them, because sort of they're the bread and butter that we use for any sort of hadron calculation. Okay, we're almost here. It's compiling. It's doing the final compilation with G++. It's about exciting as watching the grass grow, but okay. Let's see if we're going to run the test code for us. How nice. And now it's building the Python wrappers. This is what Python hooks into to talk to the C++. It's quite elaborate. I don't know who created this. If you find out, let me know. I've tweaked it a little bit. The original one, it reached out to external files in your Google Drive to pull things in. I've bypassed that to keep it simple. But okay. All right, and that has succeeded, and we have now loaded in the OHA PDF library, and you see some things there. And then I'm just doing some sanity checks to make sure everything is there and that I've got things in my directory correctly. So, okay. This OHA PDF config, that tells you all the information you need to know about the OHA PDF library. It'll show you the prefix, the include directory, the library directory. The data directory is where the PDFs are stored. That's quite important. Okay, and then let's see. Yeah, and so I'm going to install, in this case, I've installed one of the PDFs. I've installed PDF CTEX 6 L1, stands for reading order number 1. And then we're just going to define some things so I can get a hold of the gluon, the down, the up, etc. And then we're going to plot those, okay? And so, at this point, I now have access to a real PDF. I have the full X dependence, Q dependence, and then you can take your favorite PDF, you can install that, and you have full access, okay? So we've got the PDFs, but they're not done. We're going to do fragmentations because the PDF is what we use on the incoming side, and then we're going to create a pion and then fragment it. So now we need the fragmentation functions. So we're going to install the map.ff fragmentation function. Again, some definitions there so we can get a hold of those. And then I'm going to do the integration with Vegas integration routine, Monte Carlo integration routine. So that's in pip. So I'm installing Vegas, and I need alpha S. So there's the formula for it that gives me an alpha S to leading order. That's good enough. Here's my matrix element I'm going to calculate, and here's my cross section. And then you put it together. I import Vegas and set up Vegas, and now I'm actually going to calculate Vegas for a set of PTs going up from 1.5 to 19. All right, so now I'm doing a PT calculation, and it takes a while. I'm up to 13, and I have to go up to 19. We'll be there in a moment. And then all you need is the module to write the paper and send to the archive. But okay, at least we'll do the calculation for you. 16, almost there. One more. You can see it's falling like a rock. It's going from 10 to the minus 2 to 10 to the minus 10. Oh, there we go. Okay. And here is where I've imported the data. So I've imported this. I made a Python CSV file just so you don't have to use external files because they could be a little complicated. And so I do some manipulation. These are real data points. The uncertainties are fake. So this is I0 production at Phoenix versus PT. And so the real calculation. We use the PDFs, we use the fragmentation functions, we used it, and you can see it actually did it. I think I have a duplicate down here because I was just playing around a little bit. So if you look up here, I've got, I read in the, I read in the data. I just, I give it the PT in the cross section. I do not give it any uncertainties. And if you look down here, you'll find out that what I do is I use fake errors, and I use an error of 50%, just so you can see the error bars. But those are fake. If you want to do real ones, I'll show you. Let's see. Let me go back to inside of Windows Open. There we go. Here inside of extra data, there are a couple of data files, the Pi0 Phoenix. If you want to parse that data file, you can use pandas to do that. It has minus and plus statistical, systematic. If you want to put those together and put in real errors, you can do it. But just to get it to run without any external files, I sort of cheated and did that. So at this point, again, I mean, this is all, you tell me what you want. But at this point, you know how to compile LHA PDF, get the library inside of Colab. You can pull in external PDFs. You can pull in external fragmentation functions, use Vegas to do the convolution, and you get real cross sections out. So that's quite useful. And then I'm going to show you some tricks to simplify that a little bit. Let me pause there. Any questions, any problems, complications? Hopefully 1, 2, 3 should just run out of the box. So they don't depend on any external files. So you can take those home and hopefully use those as templates. Are people getting this to work more or less? Okay. All right. So let's try the next one. And number 4, so Neo PDF, and if you just Google that, that is a package. Let's take a look there. This is a new Python package. You can get it on GitLab. That's not the wrong Neo PDF. There are too many Neo PDFs later. Let's try this one. Yeah, okay, that's better. Okay, so this is a Python package written recently. It's written in Rust, but the important thing is it is in Python and it can eat the LHA PDF files. Now, the problem with what I showed you before was that this deal of downloading the LHA PDF and compiling it, that works perfectly. It just takes 10 or 15 minutes every time you want to do something. And basically, you're sort of using a sledgehammer to crack a peanut. What we really need, all we're trying to do is we're trying to get to, all we really want is to be able to load in this LHA PDF library so we can read the grid files. And what this Neo PDF does is it basically, it's in pip, and let me clear my sessions again. So, and I think that should run straight through. Basically, you can install it with pip, Neo PDF, and then I can eat the LHA PDF files. I have to use the Neo format, but it can do it. And so This example uses things, it pulls them down from the web, and then okay, let me go ahead and do that. Yeah, it looks like this one, it connects up to your local Google Drive. So you'll have to authorize that. And oops, there we go. So so that way you can download and put some PDF files in your Google Drive. And in particular, I think this is the one. What I did was on number 2, I just grabbed a slice of PDFs at Q of 10, and I shoved those in by hand. So you could look at the PDFs at Q of 10, but not any other Q. Now I'm going to link to the real PDF files. And so I've put those in my Google Drive. Let me show you where those are. On the okay. So if you want to do this, this PDF directory zip, I've put everything in there. And so let me show you what's in there. I've downloaded a few PDF sets. So I have CT10X, MSHT, and then CTEC. And here I have RS fixed and RS free. Okay. And you can make your own for NeoPDF. There's one detail they haven't documented. I need to contact the author, but you can make your own, but every file needs a index number, which is not standard, but anyway. So, but I've downloaded those and set those up. So now you can access those, and that's what we're going to do here. So I've now linked it from Google Colab Import Drive. I've imported my Google Drive, and then you can see if I look inside where I keep those in the EIC school, I have a PDF directory. And if I look in that PDF directory, specifically RS fixed, you see they're the data files. Those are the ones we generated last Friday, and then I can pull those in and look at those. And that's what I've done down below. So let's see if I've done that. Okay, here's a generic one, and then and then here's your strange distribution. So here's the strange distribution at the Q0, 1.3 for Q. And then you see the large difference between the fixed and the free. So now you have a full set of real PDFs that you can go at. So if you want to, for example, if you want to go back and make, I challenge you to make this diagram, do the momentum fraction, a few Q values to see how things change. Or if you like, you can pull in some different nuclei and do the nuclear correction factor as a function. This is Q of 10 for different nuclei. And you sort of see here, helium, helium, the nuclear correction's not so much. And when you get down to lead, it gets kind of bigger. So it sort of increases as age, you would expect. So go back. Yeah, so this is using NeoPDF. And with that, you can pull in any PDF you want. Let me show you some details. Let's see. Okay. Yeah. Here, this is the